Moin Hamburg, ich bin Artur Kondas und heute werden wir darüber reden, Need for Speed, scaling Go microservices. And believe me or not, I haven't Googled that. I've used to be able to speak German. I can't now. Blame me on that, but doesn't matter. Okay, so let's see what we'll be talking about today. So we'll be talking about a few very fun things. So is anyone writing Java in here? Okay, like 3 people, so you know premature optimization is the root of something. Then we'll be talking about how you can scale before you go live with your services. Then we'll be talking about how to benchmark first and then scale next, not the other way around because it's just plain stupid. And then we'll be talking about the actual scaling in Go microservices, which will be this async processing. Another question, who's writing Go in here? Or who wrote Go? Mega, okay, that's cool. A little bit about myself. So, as you can see from this picture, I'm very similar to myself. I'm a lead software engineer at Form 3. I'm a teacher. I taught music, coding, whatever, basically. I'm an SRE, and I'm an open source contributor. I do music, I produce music, I collect guitars, amps, pedals. If it makes sounds, then I collect it, basically. I'm a coffee junkie, a food junkie. I bake, I eat pizza, I build furniture, and all that stuff. If you've been into Docker community, you know that the end game for everybody who's doing Docker is to build furniture. We're not going to maintain Docker by 2015 or 2050. And most of all, I'm a human, as you can probably see. Okay, so there's a warning here. So although many of us here write Go in some capacity, this is a bit Go-centric talk at the very end of it. But before we will get to this part, we will be talking about like general ways how you can scale your stuff. And also, this is not the talk that will fix all of your problems with your current solutions or current stuff you're building. This is just like a happy-go-lucky kind of a pointer, go there and maybe something will happen. And if you have more things you want to chat me about scaling in general, catch me outside and then we can have a chat. Okay, so into the actual coding. So you probably heard, if you're in IT world for more than 15 minutes, there is a saying that the premature optimization is the root of all evil. And it has been written, well, more than 60 years ago, right now. And before we'll start dissecting the thing, let's see the whole quote, because it's very important to understand why Donald Knuth actually wrote it. So it says, we should forget about small efficiencies, say about 97% of the time, premature optimization is the root of all evil. There's a 80-20 principle here also hidden. So 80% of your system performance is just 20% of your work, and the other way around. So 80% of your work is just 20% of your system performance. So what you should get from that is scaling as an activity is a fun one, but starting a bit too early can actually lead to some disastrous events. And if you've been working with prod environments for more than 12 seconds, who brought down prod in their careers at least once? Okay, who did it twice? Who did it 3 times? I can actually hold my hand a bit longer than this. And 2 out of 3 of these happened because we started scaling a bit too early and then we find out some bugs, so yeah. For the sake of this talk, we'll be talking about what we do at Form 3, which is payment services. So what my team is working at, we're working at Euro services, and we're working specifically on SEPA services. So from this bit, and this is taken from the European Commission payment something. If you Google that, then you will find it. These are the numbers from 2021 because for the last 2 years they haven't been updated because they've been moving everything to a new platform. So in 2025 we will get results for 2022 and etc. etc. So first of all, the SEPA Direct Debit is the SEPA initiative, and SEPA stands for Single European Payments Area. So basically, it doesn't matter if you're in Germany, Poland, France, Spain, whatever, you can transfer your money easily as long as in euros. And then if you go outside of this, for example, Poland, we have Polish zloty, but we still can use SEPA as a means of transferring money here and there. So these are some numbers taken specifically for Germany. So in 2021, SEPA direct debit took 11,597,954,000, and there's something later on. And as you can see, this number is more or less roughly the half of all the direct debits that has happened in 2021 in the European Union. And this growth number is a bit varied depending on the source you will take it from. But for example, if you compare it to Spain, they had in between 2020 to 2021 a growth around 12%. Germany didn't have as big growth, but also, well, Germany has been leading in European payments for quite a while right now. Yeah, okay. So there's a question here. How can we improve payment processing time for maximum size files from hours to minutes? So I will try to go around the NDAs as much as I possibly can. SEPA is a batch payment processing. So you get a file that consists of millions and billions of things, and then you split it up, process them, pack them together, ship it. Super fun. And then what happens, which is like extremely unlikely thing to happen, what happens if you get more than one batch file that has maximum number of transactions within it, and then what happens when you get maximum number of files with maximum numbers of transactions, just like that, in a second? Well, if your answer is, we dead, yes, and there's no payment service that can handle that until now. Okay, so we'll get to how we did it and what we did it. There's actual code examples. So before we even start talking about how to scale upwards, we have to talk about the architecture a bit. So if you've been around tech community for more than 15 seconds, or like, okay, 20 minutes, let's say, then you will at least know this one. Who's using Kubernetes in the production services? Who's using Docker? Yeah, okay, cool. Right. So this is a very important thing, but again, this is a snake oil. If your services aren't ready for Kubernetes, nothing gonna help that. But let's start from the left-hand side corner for you. So we'll start with CQRS, which stands for Command Query Responsibility Segregation, which is a development pattern by French consultant Bertrand Meyer. I always forget that. I don't have very good memory for names. So basically, it defines a model where a single method can either retrieve data or it can modify data, but it can't do both. So you can't have a method that will both, give you the data and modify the data. It has to be one way or the other, which is actually a very nice way of how you can design the services, because then you have like a very simple responsibility schema across all the handlers for your application. So at Form3, we use that basically everywhere. Doesn't matter if that's a small internal program or a big batch gateway like a SEPA is, because it helps us to divide and conquer and scale up depending on what we need to scale. And then we have containerized microservices. So we don't have small services that does everything. We have one domain, one service, and that's all. So thanks to that, within one singular stack, if we see that we need more reads than writes, we can just split it and ramp up the read or the writes, depending on what we need. Then cloud native and cloud agnostic. If you've been in tech again for more than 20 minutes, there is a very big shift to not believing that Jeff Bezos is going to save our world or whoever. It's to have interfaces everywhere to be able to get your services from the ground up running anywhere in a matter of minutes. And this is basically what we do in Form3, which is, well, we're trying to make that happen, which is a very big and hard thing, but yeah, we kind of make it happen. And then this one actually connects to this one directly, which is messaging as communication pattern. So the way how our services are built, we don't have direct communication between services. Everything happens within the queues and topics. So any service can be a consumer of any message as long as it understands how to read the message. I hope that makes sense. It's a bit convoluted, but I hope it does. So, for example, I don't know, if I will send you a short SMS, right, to every one of you, I would have to go one by one. Or what we could do, we could set up a queue in between. I will send a message to here, and then if you want to pick it up, well, you just subscribe to the queue, take it or leave it. It's up to you. And the same happens with our services. So messaging as communication, great stuff. I will get back to this. And high observability. So before we will do anything, we have countless and countless and countless graph on the board to see how our services progress over time. How do they work? Are they healthy? Are they happy? Do they need a pet or something? So we are able to do that. And then the Kubernetes. Who built Kubernetes cluster from ground up on production here? Okay, how did you like it? Thank you. So basically, it's not extremely pleasant experience, but at the very end, if your stack is ready to build it, it is actually pretty nice. So then, on this is what we do at Phone3, and this is how you can implement it in your own world. So again, nothing is a snake oil. Take it, with a pinch of salt, and we can have a chat about it. So CQRS, your application is doing what it needs to do, nothing more, nothing less, which is, Artur, it's a really nice thing to say of you, but how can we do it? Well, you have to push back on your project managers and your CTOs and everybody and say, we need to do it right, or we can do it bad, and then we have to pay the price later on. And I found in the last years that there's a bit of a shift. So everybody starts to understand that, hey, let's build stuff once and forget about it and do it right. So this is basically your attack angle. Then containerized microservices. Does anyone listen to guitar music here? Okay, do you know Yngwie Malmsteen? He's in the 80s, he was a super fast shredder guitar player, played Bach and etc. And he says that more is always more, and more is always better, which I think is a very good example in here, which is if you have your stack containerized, and then if you need to scale it up, well, more is always better. And then it comes with money implications. If you have means to pay for your stack, and it is better, but otherwise it might not be. But then it connects really nicely into cloud-native/cloud agnostic approach, which is don't let Jeff Bezos to say, hey, you can't do this and nothing else. So if you're thinking about your stack to make it scalable in the future, think about it what you need instead of which AWS component will allow you to do it. Because short-term solution, great. Long-term solution, kind of wonky. And this, again, connects directly into messaging as communication, because if you used messaging and if you use AWS, you've been using SNS, SQS combo, which if you've used it, it's a reliable one, it's a rather good one, but then it has some limitations, and then you have to work around those limitations. So everything here you can mix and match into print out as a board game. So this one will allow you to send one thing into multiple places or multiple things into one place, but like a funnel which goes both ways. Kubernetes, I've said it before, I've said it again. Use it when you really need it. Again, we know we've built some clusters, and it is an experience, let me tell you that. I've built a few in my career, and yeah. And then the high observability thing, which is if you understand your systems from start to finish, then you're a happy man, or a happy woman, or a happy human. because you know how everything connects together. But then, how does that apply to our service? And this is when we will go back into the separate DD, separate direct debit example, which is the issue that we had last year, where we found a small bug, or maybe not a bug. We just never reached the place where we will have to fight with the maximum file size. So then we developed a thing which is called benchmark first and then scale next. So instead of doing the guess game and going, hey, this works, this doesn't, this is fun, this is not, let's actually check it out and see what's what. So there's 4 steps into our approach. The first one is load test. So we want to basically apply some chaos theory into our application to see how fast can we break it and what we have to do to break it. And then we can, divert into seeing, okay, can we break it with the least amount of resources? Can we break it with the max amount of resources? Which way? Once we do that, then we start to analyze it. So we need to see if the output from our service is what we expected it to be. If it was, then we are a happy man. If it wasn't, then we have to start thinking what went wrong. So we found what went wrong via load test. Let's go to the apply. So we need to start with the simplest and fastest solution because, as you know, more often than not, we don't have time in order to do, in order to do big things. We kind of have to poke the bear in small places, and then it, as a compound effect, it works better. And then the replay, so everything back again, do the load test, analyze, and see if it changed. If it changed, move on. If it didn't, you have to do it again. So I can give you a small peek into one of our load tests. So this is not a good sign. If you've seen it in production, this is the database. These are the commands we had on one of the gateways. If you've seen these in your production service, it means trouble. And it means sleepless nights, and it means being on call and being actually really sad person. So what happened? On the command screenshot, you can see how rammed our service was. And it was rammed in a very specific way. Because the first one is some arbitrary command that runs throughout the life cycle of the whole batch processing. And then the second one and the third one, because there's a green one and there's a purple one, and then if they combine together, they do this Q-ish thingy. So you can see that we started really high, something happened, and then we stagnated throughout 3/4 of the whole processing. It is not good. And then if you connect it to database, this is where all hell breaks loose, because this is basically on the same time frame and on the same volume. So it starts relatively normal and happy, and everybody is happy. And then somewhere in here, which has no correlation to comments whatsoever, it just decides, okay, 110% of database resources? Why not? And then it does that. So we ended up being in this small pickle where we had to figure out what happened. So we started with 3 usual suspects. So the first one, as you see in the database peak, we went with, is it the database? Is the database to blame of all the things? So we need to discover what is the culprit of this, and maybe we'll be able to find the issue, the core one that made the whole service clog as it did. Or maybe the commands are to blame. Maybe because it goes from 0 to 100 constant, and it doesn't change apart from that 3/4 thingy. Maybe there was somewhere there that was clinging to something else, so we need to find that. And then the funniest thing to debug ever, which is stack. What if the stack was to blame? What if the whole application was just perfect, chef's kiss, but then the stack didn't pan out? So we actually checked the database. There was some things in the database. We did it. We checked the stack. Happily, it was OK. But then we checked the application. And then the application had one bit where it wasn't able to go asynchronous. So everything that happens in, although we had messaging services, etc., again, SNS, SQS, it can clog a bit in like weird places. So what we had to do, we had to go outside there, go into the application, and see what happens. So this is the part with the codes, which is here. Can you see that? Yes. Is the size of this okay? Can you see it? Do you need to be larger? Cool. Okay, a bit larger. S'il vous plaît. Good? Cool. Okay. So if you can't see it by now, I like Terminal, which I like Vim. And we can have a chat about that later, about the setup and etc. If you use Vim, I always like to chat about it. Okay, so there's three things. So in Go, when you want to do asynchronous processing, you use Go routines. And the Go routines are single-threaded things. You can spawn, they will do something, die off. Super fun. The issue with Go routines is you don't have any control about them whatsoever if you don't implement it. So the way how Go is written, if you've written Go or if you haven't, Go is written in a way that it believes that the developer should have the most tools as they want. So if you need something, you can write it, implement it. You don't have a magical package, which is not true because I will show you in a second. And then you have to build it yourself, and then you have full control of it. Okay, so let's start with the semaphore. Have you heard about the semaphore pattern in Go? Okay, cool. So let me show you what that is. Semaphore. So we have an absolute dead simple application. So let me show you from the bottom. So we will have a channel, right, that has a struct. And the struct, think about it as our token. So we will allow the application to take 2 tokens at each iteration, at each tick of the compiler, to say, okay, I have 2 tokens, I can use them to spawn Go routines. So I'll spawn some Go routines, I will wait 3 seconds for all the Go routines to finish, and then I will tell on the terminal, all work is done. Okay, super fun. And then on the top of it, we have the actual worker. So we take the token at the very beginning of it, and then defer is basically a promise that when we finish processing, we'll give back the token. So as you can see, we are doing extreme hard work because we are sleeping for a second. And then what happens on line 22 and 23, I have an array on the top which counts all the workers, so we can actually see how the processing went. And I will just print out a log message, I've finished my work. Does that make sense? Any questions so far? No? Yes? Okay, cool. So let's do the magical go run. Let's clear the go run. Okay. So remember, we have 3 seconds. We have Go routines from 1 to 10. So in total, we have 9 Go routines. Yeah, 10 actually, because 10 is also a number. So after 3 seconds, you can actually see that we have only 4 Go routines that has finished. You can see that number 8 has started, but it hasn't finished before the application went down. And the 9 has started, but it hasn't finished before the application went down. What happens in Go is that if you want to be 100% sure that your application finishes whatever it does on the Go routine end of things, you have to tell explicitly, please wait. Just like, do me a favor and wait. So we could have, I don't know, make a check on the array, and unless it has 10 members, we won't finish. But we didn't do that. Okay. So then the solution is to use semaphore in conjunction with a wait group. Do you know what a wait group is in Go? Okay, I can see like 50-50 head movements, so let's talk about it. So, bam, 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 bam. Okay, the main difference right now between the code that we had like 1 minute ago is the line 36 and actually line 33. So in Go, you have an ability to set up wait groups. So you have an ability to say within the code, hey, please wait. Just like block the processing and please wait for me until I finish. So I'm going with, okay, every time I do an iteration, just add one Go routine and just add one token into the wait group and wait until all the wait groups are depleted. So internally it works that unless the wait group is not empty, I will continue processing. When it's empty, I will finish the processing. So on the top, well, nothing really changes because the processing is, again, the same, with the only difference is on line 18, we go, okay, I've finished. I can mark this token as done, and that's all. So remember last example, we had 3 seconds, and within those 3 seconds, we had to do 10 operations, which we didn't. As you can see, we don't have the time in here, because that was an example. And then, if I wouldn't have the wait group right now, when I run it, it will go, okay, I finished. Maybe the tick within the compiler was able to spawn some Go routines. Maybe it wasn't. It's basically a flip of a coin. But I want to be actually 100% sure that I will spawn all the Go routines, and then I will have what I want. Okay, so let's start this. This is always the fun part when you have live coding, where it's like somebody starting something, and then you have to wait for it to finish. So as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I forgot about a 10. So that's actually on me. There's a bug in the code. So what you can see in here, that within our processing time, we actually made the application explicitly wait until all the Go routines are finished. So it has to wait. And this is the approach which we did within our processing. So instead of spawning 10 Go routines, we went way higher than this. And we found the perfect balance between the messages in the queue and spawning Go routines within the application in order to make everything super smooth and super fast. But then, okay, we had to implement that ourselves. What if there's something that we could do in order to unify our approach across all the applications and do it with something that is somewhat maintained by the Go community, which is like a very big case in Go, that if it's something maintainable by the community, everybody's happy. So I want to show you first the implementation, which is here. Okay. So there's like, this is what is important. So right now I'm setting up context, and we can have a chat about context, but it's not relevant right now. Context is basically a way in Go how you can inform the system about how healthy the system is. Think about it this way. But at the very beginning of it, we go error group with context. And error group dot with context is basically what we've implemented ourselves 2 minutes ago. So instead of right now writing the same codes all around every microservices that we have a package that will do it for us and more. The implementation is basically one-to-one with what we had on the previous slide. And we still have to set up the semaphore, because we need to say to the error group how many concurrent items you want to have processing. So this application is that simple. It will fetch those 5 URLs, which one of them is my blog if you want to read my ramblings about stuff. You can guess which one this is. It's not Quadser, but I would like it to be. And then, just so you know, this is how the how the code to fetch those sites work. So we're building a new request with a method get. We are building them with context because we want to be able to finish if the request hangs. And then we're trying to fetch it. We're copying all the output into, or like the we are copying the size of the body into the output, so to see that we actually fetched something, and then we discard everything else. Because we could have kept it there, but then memory leaks and etc. So we didn't want to do it. Okay, so clear, go run again. And as you can see, it will work exactly the same, with the only difference right now that the use case is a bit different because doing numbers when you have more sophisticated approach, I don't think it actually adds up. So you can see every single page right now was spawned as a Go routine and fetched as a Go routine. And then every single one is absolutely independent from each other. And the application will wait until you will get it all. Does that make sense? Any questions so far? Okay, cool. So we can go back into the slides. Yes. So by using error groups, this is actually very nice title of something. But by using error groups, we're able to run thousands of tasks concurrently in each application and improving the application speed by 90%. It doesn't feel like much code, but again, if you go back into benchmark first, scale next, we found this as the major culprit of all the issues that we had in the application. So that was the easiest and the fastest bit we could do. And we actually did it this way. So we did our own implementation at the very beginning, saw if it works, and then tried to find something which is a bit more robust than our implementation because, frankly, we didn't have time to build it ourselves and maintain it ourselves in-house. But again, not all scalability comes from clever code. So this one, we can argue if that approach was clever or not. But sometimes just like a small change will be enough to make the application faster. Does anyone played GTA 5 here? Okay, have you played GTA Online? Okay, so in GTA Online, there is a bug which I don't think has been fixed by Rockstar for, 11 years since the game was released? Somehow. So when you log into GTA Online, it will hang for a second, or for 2 minutes, or 5, depending on how fast your connection is. What happens in the background is a very messy implementation of JSON parser. And this is the only reason. And the solution is already there. And if you have a PC copy of GTA, and if it's legal, then you can change that, and then it will parse the code that goes into your game way faster. And the change, if I'm correct, was literally 17 lines of code within the code base, which is dead massive. So if you need to take anything out of this talk, it's like the 4 principles of scaling. So go big, try to break it. Don't do it on production because don't. But take one environment, try to break your application as fast as possible and as bad as possible. Then see what went wrong, then go slow and be extremely meticulous about what things can improve, and then scale up, and then implement those things, do it all again. And this can be a fun exercise that you can go and on and on and on and on. And you can make your application way funkier. If you want to chat about scaling food, guitars, or anything, I will be around here munching stuff and drinking coffee. So feel free to reach out. Thank you.
Big congratulations. I think you covered so much ground in 30 minutes. I'm in awe right now. We received some really interesting questions, which I'd like to take a few minutes to answer. Which tools are you using for load testing?
Okay, so we do actually our custom in-house tools. So we wanted to understand every single approach. So first with our code, and then with whatever we tested, we actually had some time to build our own testing solutions, which basically what they do is a bit around Chaos Monkey from Netflix. So like go into the code and just try to trash it. And then a bit about DDoSing our own services. So we're trying to send as much as we possibly can in the shortest amount of time, just nuke it. Yeah.
The second question is, did you find a sweet spot of concurrency limits in connection to CPU threads regarding scheduling?
Yes, whoever asked it, yes. There is an actual sweet spot with AWS instances and the concurrency. And we had to fight tooth and nail to find it, but we have like a wiggle room. So if the instance, for example, will right now change, our application is smart enough to go, depending on, it will understand on which machine it works, and then it will go up or down because it has an ability to self-heal and just adjust however it sees fit.
And then the very last question, did you, spawning all those single threads on mass produces garbage collection, or did you optimize for hardware?
Okay, so coming back to what I said right now, we kind of did optimize, but then when we started implementing the multiple threads, we actually went with a bit of clever approach how we are able to clean up the application as it goes. So it's not willy-nilly error groups just go and maybe some tweaking on the hardware and the concurrency. We actually went into garbage collector on Go. If you don't know, or if you know, garbage collector in Go is automatic, but you can tweak it to your own liking. So we actually did tweak it a bit. So whenever the processing is finished, we explicitly say this message goes to the bin and then pick up another one. So we are able to maintain limits depending on the hardware instance on AWS, however we see fit.
Awesome. Give one more round of applause for Artur, please.